In this video, we'll solve the numericals on tractive effort and specific energy consumption. Problem statement: a 256-ton motor coach train with 4 motors takes 20 seconds to attain a speed of 40.25 km per hour starting from rest on a 1% up gradient. The gear ratio is 3.5, gear efficiency is 95%, wheel diameter is 91.5 cm, train resistance is 44 Newton per ton, and rotational inertia is 10% of the dead weight. Find the torque developed by each motor. So we have the following data given. Weight of the train is 256 ton. We have 4 motors. Maximum speed Vm is 40.25 km per hour and T1 equal to 20 seconds. Gradient percentage G is 1%. Gear ratio gamma is 3.5. Gear efficiency neta is 95%. Wheel diameter D is 91.5 centimeter, that is equal to 0.915 meter. Train resistance R equal to 44 Newton per ton. Rotational inertia is 10%, therefore WE is 1.1 times W. The accelerating weight WE is 1.1 times W. Tractive effort on the driving wheel is given by Ft equal to 2 neta T gamma by D. Using this equation, the torque developed by the motor can be found. We have the tractive effort for the propulsion of the train given by Ft equal to 277.8 We alpha plus 98.1 Wg plus Wr. We have We is equal to 1.1 times W, that is 1.1 times 256, and we have T1 equal to Vm by alpha. Therefore alpha is Vm by T1, that is 40.25 by 20, that is 2.0125 km phps, kilometer per hour per second. So substituting the values in the equation of Ft, we get 277.8 into 1.1 into 256 plus into 2.0125 plus 98.1 into 256 plus 256 into 44. Solving for the equation of Ft, we get Ft equal to 193812.416 newtons. So this value can be substituted in the equation of tractive effort on the driving wheel. That is Ft equal to 2 neta T gamma by D, which implies T is equal to Ft D by 2 neta gamma, that is 193812.416 into 0.915 by 2 into 0.95 into 3.5. So we get the answer as 26,667.4 Newton meter. So this is the total torque developed by the motors. Therefore, torque developed by each motor is T by the number of motors, that is 4. So we 26,667.4 divided by 4, we get it around 6,666.8 Newton meter. Next problem. A 203-ton motor coach train has motors each developing a shaft torque of 5130 Newton meter during the acceleration period. Calculate the time taken by the train to attain a speed of 42 km per hour starting from rest on a gradient of 1 in 250. The motors have a gear ratio of 3.5 to 1 and gear efficiency is 93%. The wheel diameter is 91.5 cm and train resistance is 45 Newton per ton. Allow 10% for the effect of rotational inertia. We have W equal to 203 ton. Torque developed by each motor is 5130 Newton meter. Maximum speed Vm is 42 km per hour. Percentage G is 1 by 250 into 100, that is 0.4. Gear ratio gamma is 3.5. Gear efficiency is 93%. Wheel diameter is 91.5 centimeter, that is 0.915 meter. Train resistance R is 45 Newton per ton. Rotational inertia is 10%. So WE is 1.1 times W. We have Ft equal to 277.8 WE alpha plus 98.1 Wg plus Wr, that is equal to 277.8 into 1.1 into 203 into alpha plus 98.1 into 203 into 0.4 plus 203 into 45, so that we get it as 62,032.74 alpha and plus 1700.72. So Ft is equal to 62,032.74 alpha plus 1700.72 newtons. So we have the torque developed by each motor as 5130 Newton meter. So torque developed by each motor is given as 5130 Newton meter. Assume the number of motors as 4. We get the total torque developed equal to 5130 into 4, which is equal to 20,520 Newton meter. We have the tractive effort Ft equal to 2 neta T gamma by D, that is equal to 2 into 0.93 into torque value, that is 20,520 into gamma, that is 3.5 by 0.915. So we get it as 145,994.75 newtons. So substituting the value of Ft in the equation of Ft for the propulsion of train, we get 145,994.75 is equal to 62,032.74 alpha plus 17,100.72. So solving this, we get the acceleration value alpha equal to 2.078 kilometer per hour per second. So we have the time for acceleration T1 equal to Vm by alpha, that is equal to 42 by 2.078. So we get the time duration for acceleration period as 20.21 seconds. Next problem, an electric train has an average speed of 42 km per hour on a level track between stops 1400 meter apart. It is accelerated at 1.7 km per hour per second and is braked at 3.3 km per hour per second. Draw the speed time curve for the run and estimate the energy consumption at the axles of the train per ton kilometer. Take tractive resistance as 50 Newton per ton and allow 10% for rotational inertia. So we have the given data. Average speed VA is 42 km per hour. Distance between stops is 1400 meter, that is 1.4 km. Acceleration alpha is 1.7 km per hour per second. Braking retardation is beta 3.3 km per hour per second. Tractive resistance R is 50 Newton per ton and rotational inertia is 10%. Therefore, WE, the accelerating weight, is 1.1 times W, the dead weight. The speed time curve considered for the train run is trapezoidal speed time curve as shown. So from the equation of VA, that is 3600 d by t, we can find the actual time of run t equal to 3600 d by VA, that is equal to 3600 into 1.4 by 42. So the time of run is 120 seconds. For the trapezoidal speed time curve, we have the equation of maximum speed Vm equal to T by K minus square root of T by K square minus 7200 D by K, where K is equal to 1 by alpha plus 1 by beta, that is equal to 1 by 1.7 plus 1 by 3.3, that is 0.892. Therefore, we have Vm equal to 120 by 0.892 minus square root of 120 by 0.892 the square minus 7200 into 1.4 by 0.892. Solving this equation, we get the maximum speed Vm equal to 52 km per hour. So the time for acceleration T1 is given by Vm by alpha, that is 52 by 1.7, which is equal to 30.6 second, and time for retardation T3 is Vm by beta, that is 52 by 3.3, that is 15.8 second. Time for free running T2 is equal to T minus T1 plus T3, that is 120 minus 30.6 plus 15.8, that is equal to 73.6 second. Next, we have the specific energy consumption given by the equation 0.01072 Vm square by D into We by W plus 0.2778 R D1 by D in watt hour per ton kilometer. We have D1, that is the distance traveled during acceleration and free running period, calculated by equation D minus distance during retardation. So D1 is nothing but total distance traveled D minus distance traveled during retardation. So that is 1D minus half Vm T3 by 3600, that is 1.4 minus half into 52 into 15.8 by 3600. So we get the value of D1 as 1.284 kilometer. So next, the specific energy consumption we have equal to 0.01072 into 52 square into 1.1 by 1.4 plus 0.2778 into 50 into 1.284 by 1.4. So solving this, we get the specific energy consumption as 35.51 watt hours per ton kilometer. Next problem, an electric train accelerates uniformly from rest to a speed of 48 km per hour in 24 seconds. It then coasts for 69 seconds against a constant resistance of 58 Newton per ton and is braked at 3.3 km per hour per second in 11 seconds. Calculate acceleration, coasting retardation and schedule speed if the station stops are of 20 seconds duration. What would be the effect on the schedule speed by reducing the station stop to 15 seconds duration? Allow 10% for rotational inertia. We have the data given. V1 is equal to 48 km per hour, T1 equal to 24 seconds, T2 equal to 69 seconds, T3 equal to 11 seconds, beta equal to 3.3 km per hour per second, R equal to 58 Newton per ton, Ts equal to 20 seconds, rotational inertia is 10%, so We is 1.1 times W, and we have to find the schedule speed Vs when the time of stop is 15 seconds also. So the speed time curve considered is the quadrilateral speed time curve. So the acceleration alpha is given by V1 by T1, that is 48 by 24. So alpha is 2 kilometer per hour per second. We have the time duration for braking retardation T3 equal to V2 by beta. So the speed attained at the end of coasting period V2 is equal to beta into T3, that is equal to 3.3 into 11, that is 36.3 kilometer per hour. We have the time for coasting period T2 equal to V1 minus V2 by beta C. Therefore, the coasting retardation beta C is equal to V1 minus V2 by T2, that is 48 minus 36.3 by 69. We get the value as 0.19 kilometer per hour per second. Next, we have the schedule speed Vs equal to 3600 d by t plus ts. The total distance traveled during the run d is equal to half v1 t1 by 3600 plus half v1 plus v2 into t2 by 3600 plus half v2 t3 by 3600. So d is equal to half into 48 into 24 by 3600 plus half into 48 plus 36.3 into 69 by 3600 plus half into 36.3 into 11 by 3600. We get the answer as 0.16 plus 0.807 plus 0.055. So the distance traveled is 1.022 kilometer. So Vs equal to 3600 d by t plus ts. So for a station stop of 20 seconds, we get Vs equal to 3600 into 1.022 by time duration 104 plus 20. So we get the answer for schedule speed as 29.67 kilometer per hour. Schedule speed for a station stop of 15 seconds is Vs equal to 3600 into 1.022 by 104 plus 15. So we get the schedule speed as 30.917 kilometer per hour. So reducing the station stop has increased the schedule speed. Thank you.